Hello there, and welcome to the Slumbering Archive. I'm so glad you found your way here tonight. Maybe you've had a long day. Maybe your mind has been racing with thoughts that won't quite settle. Or maybe you're just looking for something gentle to listen to as you drift off. Whatever brought you here, you're in the right place. Tonight, we're going on a quiet journey through our home galaxy, the Milky Way. We'll explore the vast spiral of stars and dust and mystery that stretches across our night sky. And you've got nothing to do but rest. Let your mind wander through these cosmic landscapes. Let the facts wash over you like waves. There's no test tomorrow, no need to remember everything. Just listen and let yourself drift. We'll move slowly tonight. There's no rush. The Milky Way has been here for billions of years, and it'll be here long after we're done talking about it. So settle in, get comfortable, and let's begin this exploration together. If these nighttime explorations help you unwind, consider subscribing to the Slumbering Archive. It helps others who are searching for something calm and contemplative to fall asleep to. And I'm curious, where are you listening from tonight? Are you looking up at the Milky Way from your own corner of the world? Then let's talk about our galaxy. The Milky Way is home. That's the first thing to understand. When we look up at the night sky and see that hazy band of light stretching from horizon to horizon, we're looking at our own galaxy from the inside. We're not observing it from some distant vantage point. We're embedded within it, like a person standing in the middle of a vast forest, trying to understand the shape of the whole woodland. The name itself, Milky Way, comes from ancient Greek mythology. They called it Galaxias Kyklos, the Milky Circle. The Romans called it Via Lactea, the Road of Milk. The story goes that the goddess Hera spilled breast milk across the heavens, creating that luminous band. Different cultures had different names, different stories, but they all noticed that river of light in the darkness. Think about that for a moment. Every civilization that looked up saw that band and tried to explain it. Our galaxy contains somewhere between 100 billion and 400 billion stars. The exact number remains uncertain because many stars are hidden behind dust, and many are too dim to detect even with our most powerful telescopes. But let's settle on the middle estimate, around 200 billion stars. That's 200,000 million suns, each one a nuclear furnace, each one potentially hosting its own family of planets. 200 billion stars. And we've only just begun to understand what's out there. The Milky Way is a spiral galaxy. From above, if you could somehow float above the galactic plane and look down, you'd see a beautiful spiral structure with arms curving outward from a central bulge. It would look something like a cosmic pinwheel spinning slowly through space. The spiral arms are brighter than the regions between them because that's where new stars are being born, where gas and dust are compressed and heated until fusion ignites. Our sun sits about 26,000 light years from the Galactic Center. We're not in the center, not in the suburbs exactly, but somewhere in between. We're located in what astronomers call the Orion Arm, or sometimes the Orion Spur, a minor spiral arm that branches off from one of the major arms. It's a comfortable spot, relatively speaking. Not too close to the chaotic center, not too far out in the lonely edges. 26,000 light years. That means the light we see from the center of our galaxy left there 26,000 years ago, when humans were still living in small hunter-gatherer groups, when the Ice Age was beginning to recede. The Milky Way is rotating, Everything in it is moving, orbiting around the galactic center. Our sun and solar system move at about 514,000 miles per hour relative to the galactic center. That's not a typo. 500,000 miles per hour. And yet, because the galaxy is so vast, it takes our sun approximately 225 to 250 million years to complete one orbit. Astronomers call this a galactic year, or sometimes a cosmic year. Think about that. The last time our sun was in this position in the galaxy, dinosaurs hadn't yet appeared on Earth. The entire age of dinosaurs, their rise and extinction, happened in just one galactic year. We've only gone around once since then. The center of the Milky Way contains a supermassive black hole called Sagittarius A. That's Sagittarius A star, named after the constellation where it appears from our perspective. This black hole has a mass equivalent to about 4 million suns, all compressed into a region smaller than Mercury's orbit. It sits there at the heart of our galaxy, pulling everything around it into a cosmic dance. 4 million solar masses. And yet, it's relatively quiet these days. It's not actively feeding on much material. Most supermassive black holes at the centers of galaxies are either actively consuming matter and blazing with energy, or they're dormant like ours. Sagittarius A falls into the quiet category, though it does occasionally flare up when something falls into it. The existence of this black hole was confirmed through decades of careful observation. Astronomers tracked individual stars orbiting near the galactic center, watching them swing around an invisible point at incredible speeds. One star, called S2, orbits Sagittarius A in just 16 years. By tracking its motion, scientists could calculate the mass of the object it was orbiting. The conclusion was inescapable. Only a supermassive black hole could account for what they were seeing. The Milky Way is roughly 100,000 to 180,000 light-years in diameter. The exact size depends on where you draw the boundary, which is harder than it sounds because galaxies don't have sharp edges. They fade gradually into intergalactic space. But the main disk of stars, the part we think of as the galaxy proper, is about 100,000 light-years across. 100,000 light-years. Light, moving at 186,000 miles per second, takes 100,000 years to cross our galaxy. If you tried to drive across the Milky Way in a car going 60 miles per hour, never stopping, never slowing down, it would take you about 1 trillion years. The universe itself is only about 14 billion years old. You'd need the universe to live 70 times longer than it already has. The disk of the Milky Way is thin compared to its width. It's only about 1,000 light-years thick in most places, though it bulges out to about 12,000 light-years near the center. If you scaled the galaxy down to the size of a CD, the disk would be about as thin as a sheet of paper. We live in a very flat structure, relatively speaking. Above and below the main disk, there's something called the galactic halo. This is a roughly spherical region containing old stars, star clusters, and dark matter. The halo extends much farther than the visible disk, perhaps 130,000 light-years or more in radius. It's a dimmer, more diffuse region populated by ancient stars that formed when the galaxy was young. The Milky Way contains roughly 200 billion to 400 billion stars, as we mentioned, but it also contains vast amounts of interstellar medium. That's the gas and dust between the stars. Most of this is hydrogen, the simplest and most abundant element in the universe. There's also helium and traces of heavier elements created inside stars and scattered when those stars died. This interstellar medium isn't evenly distributed. It clumps into clouds, some cold and dark, others warm and glowing. The densest clouds are stellar nurseries, places where gravity is pulling gas together to form new stars. The Milky Way creates about 3 to 7 new stars every year. That might not sound like much, but over millions of years, it adds up. 3 to 7 new stars per year. Right now, somewhere in our galaxy, a cloud of gas is collapsing. Somewhere, nuclear fusion is igniting for the first time. Somewhere, a new sun is being born, and we'll never know its name or see its light. Our galaxy has a distinctive bar structure at its center. For a long time, astronomers weren't sure if the Milky Way was a barred spiral galaxy or a regular spiral galaxy. But observations, particularly from infrared telescopes that can peer through dust, revealed a bar-shaped concentration of stars stretching across the Galactic Center. This bar is about 27,000 light-years long and helps funnel gas toward the center, potentially feeding star formation. The bar rotates too, but at a different rate than the rest of the galaxy. It's like having 2 clocks running at different speeds. The dynamics are complex, and scientists are still working out exactly how the bar influences the evolution of the galaxy as a whole. The Milky Way has several major spiral arms. The exact number depends on how you define them, but most astronomers identify 4 major arms: the Perseus arm, the Scutum Centaurus arm, the Norma arm, and the Sagittarius arm. Our Sun sits in the Orion Spur, which lies between the Perseus and Sagittarius arms. These spiral arms aren't rigid structures. Stars and gas don't stay in the arms forever. Instead, the arms are density waves, regions where matter temporarily bunches up as it orbits the galactic center. It's like a traffic jam on a highway. The cars move through the jam, but the jam itself persists. Stars drift into the spiral arms, spend some time there, and then drift out again. The Milky Way is not alone. It's part of something called the Local Group, a collection of more than 50 galaxies bound together by gravity. The Local Group spans about 10 million light-years and contains 3 large spiral galaxies: the Milky Way, Andromeda, and Triangulum. The rest are smaller dwarf galaxies, some with just a few million stars. Andromeda is our nearest large galactic neighbor, about 2.5 million light-years away. It's slightly larger than the Milky Way, containing perhaps 1 trillion stars. On a clear, dark night, away from city lights, you can see Andromeda with your naked eye. It appears as a faint, fuzzy patch in the constellation Andromeda. That fuzzy patch is a galaxy. You're seeing light from 1 trillion suns, photons that travel for 2.5 million years to reach your eye. The Milky Way and Andromeda are moving toward each other. Gravity is pulling them together at about 250,000 miles per hour. In about 4 to 5 billion years, they'll collide. Or rather, they'll merge. Galactic collisions aren't violent crashes like car accidents. Galaxies are mostly empty space. So when they collide, the stars pass by each other like ghosts. But gravity pulls everything into chaos, and over hundreds of millions of years, the 2 galaxies will merge into a single, larger, elliptical galaxy. Astronomers have already given this future galaxy a name: Milky Way, or sometimes Milkdromeda, a blend of Milky Way and Andromeda. Our distant descendants, if any exist, will live in Milkomeda, a galaxy that looks nothing like the Milky Way we see today. 4 to 5 billion years from now, the sun will be nearing the end of its life by then, swelling into a red giant. Earth might not survive, but the collision itself, paradoxically, won't be the problem. The vastness of space means the sun and Earth could sail through the merger relatively unscathed, at least from direct stellar impacts. The Milky Way has swallowed other galaxies in the past. We can see the evidence in streams of stars that don't quite fit the galaxy's overall motion. These are tidal streams, the remnants of dwarf galaxies that wandered too close and were torn apart by the Milky Way's gravity. The stars from those galaxies still orbit the Milky Way, but now they're scattered across the sky in long, thin filaments. One of the most significant of these past collisions was with a dwarf galaxy that astronomers call Gaia Enceladus, or sometimes the Kraken. This collision happened about 8 to 11 billion years ago, when the Milky Way was much younger. The impact was violent enough to heat up the Milky Way's disk and scatter stars into the halo. Many of the old stars in the halo today actually came from Gaia Enceladus 8 to 11 billion years ago, before the sun existed, before the solar system formed. The Milky Way was already here, already eating other galaxies, already churning with stellar birth and death. The Milky Way contains globular clusters, dense spherical collections of stars that orbit the galaxy like satellites. There are about 150 known globular clusters in the Milky Way, though there may be more hidden behind dust or lurking in the halo. Each cluster contains anywhere from tens of thousands to millions of stars, all packed into a region just a few dozen light years across. Globular clusters are old, very old. Most of them formed 10 to 13 billion years ago, not long after the galaxy itself. The stars in globular clusters are ancient, metal-poor stars from the early universe. Studying them gives us a window into the galaxy's past, into the conditions that existed when the Milky Way was young. If you could stand on a planet in the middle of a globular cluster, the night sky would be astonishing. Thousands of stars would be close enough to cast visible shadows. The sky would never be truly dark. It would be a realm of perpetual twilight, a place where stars crowded so close together that planetary systems might not even be stable. The Milky Way is part of a larger structure called the Virgo supercluster, or it was until recently. Newer observations and better mapping techniques reveal that we're actually part of an even larger structure called the Laniakea supercluster. Laniakea is a Hawaiian word meaning immeasurable heaven, and it contains about 100,000 galaxies, including our local group, the Virgo cluster, and many others. Laniakea spans about 520 million light years. That's 500 million light years, a distance so large it becomes almost meaningless. And yet, it's just one supercluster among millions in the observable universe. We are nested within nested structures, each one vaster than the last. The Milky Way moves through space as part of Laniakea, flowing toward a gravitational attractor called the Great Attractor. This is a region of space with an enormous concentration of mass, pulling galaxies toward it. We can't see the Great Attractor directly because it's hidden behind the plane of the Milky Way, obscured by dust and stars. but we can measure its gravitational influence. Beyond the Great Attractor, there's an even larger structure pulling on Laniakea. Astronomers call it the Shapley Attractor, or the Shapley Concentration, a massive supercluster about 650 million light-years away. These are currents in the universe, rivers of galaxies flowing through cosmic voids. The Milky Way is moving through space at about 1.3 million miles per hour, relative to the cosmic microwave background, the afterglow of the Big Bang. That's our absolute motion through the universe. It includes the rotation around the Galactic Center, the motion of the local group, the infall toward Virgo, and the pull of the Great Attractor. We're moving in multiple directions at once, like a leaf caught in swirling currents. And yet, we don't feel any of it. We're moving with it, falling freely through space, cocooned by gravity's gentle grasp. The Milky Way's disk contains different stellar populations. Astronomers divide stars into population 1, population 2, and the theoretical population 3. Population 1 stars, like our Sun, are young and metal-rich, formed from yeast that was already enriched with heavy elements from previous generations of stars. Population 2 stars are older and metal-poor, formed when the galaxy was younger and fewer heavy elements existed. Population 3 stars, if they existed, were the very first stars in the universe. They formed from pure hydrogen and helium, with no heavy elements at all. None have been observed, and it's unlikely any still exist. They would have been massive, short-lived, and violent, burning through their fuel in just a few million years before exploding as supernovae. The Milky Way has been forming stars for almost its entire existence, but the rate of star formation has varied over time. It was higher in the past when the galaxy had more gas available. These days, the star formation rate has slowed. We're not making as many new stars as we used to. Eventually, in the far future, the Milky Way will run out of gas. Star formation will cease. The galaxy will slowly fade as its stars burn out one by one, leaving behind white dwarfs, neutron stars, and black holes. But that's trillions of years away. For now, the galaxy is still alive, still vibrant, still making new stars. The Milky Way contains planets, lots of planets. For most of human history, we didn't know if other stars had planets. But starting in the 1990s, astronomers began detecting exoplanets, planets orbiting other stars. The first confirmed exoplanet around a sun-like star was discovered in 1995. Since then, we've found thousands. Current estimates suggest that nearly every star in the Milky Way has at least one planet. That means there are hundreds of billions of planets in our galaxy. Some are gas giants like Jupiter. Some are rocky worlds like Earth. Some orbit close to their stars, tidally locked with one side always facing the sun. Others drift in the cold outer regions, frozen and dark. And some, a precious few, orbit in the habitable zone. That's the region around a star where liquid water could exist on a planet's surface. Water, as far as we know, is essential for life. At least, it's essential for life as we understand it. How many habitable planets are there in the Milky Way? The estimates vary wildly, but a conservative guess might be tens of billions. Tens of billions of worlds where the temperature is just right, where water could flow, where life might emerge. Are we alone in the galaxy? We don't know. Despite decades of searching, we haven't found any evidence of extraterrestrial life. No radio signals, no techno-signatures, no alien artifacts. The Fermi paradox asks, if the galaxy is so old and so large, where is everybody? Maybe life is incredibly rare. Maybe it's common, but intelligence is rare. Maybe civilizations destroy themselves before they can spread. Maybe they're out there, but we just haven't found them yet. Or maybe we're truly alone, the only conscious beings in a vast, indifferent cosmos. It's a humbling thought either way. The Milky Way is surrounded by a halo of dark matter. We can't see dark matter. It doesn't emit light or interact with electromagnetic radiation. But we know it's there because of its gravitational effects, stars said. The edges of the galaxy move faster than they should based on the visible matter alone. Something invisible is adding extra gravity, keeping those stars bound to the galaxy. Astronomers estimate that about 90% of the Milky Way's mass is dark matter. The stars, the galaxies, the dust, the black hole at the center, everything we can see, that's just percent of the galaxy. The rest is dark matter, a mysterious substance that permeates the universe. We don't know what dark matter is made of. It's one of the biggest unsolved mysteries in physics. It could be exotic particles that don't interact with ordinary matter. It could be something weirder. For now, it remains a ghost in the machine, unseen but essential. The Milky Way has a magnetic field. It's weak compared to Earth's magnetic field, but it spans the entire galaxy. This magnetic field is generated by moving charged particles, particularly electrons spiraling through space. Cosmic rays, high-energy particles from supernovae and other violent events follow the magnetic field lines, spiraling along them as they travel through the galaxy. The galactic magnetic field influences star formation, the structure of interstellar clouds, and even the paths of cosmic rays. It's part of the invisible architecture of the galaxy, one more layer of complexity in an already complex system. The Milky Way's spiral arms are rich in star-forming regions. These are places where gas and dust are dense enough for gravity to pull them together into new stars. One of the most famous star-forming regions in the Milky Way is the Orion Nebula, about 1,350 light-years from Earth. It's visible to the naked eye as a fuzzy patch in Orion's sword. The Orion Nebula is a stellar nursery. Inside, hundreds of new stars are being born. The nebula glows because ultraviolet light from young, hot stars ionizes the surrounding gas, causing it to emit visible light. It's a beautiful, chaotic place, full of protostars, protoplanetary disks, and the raw materials of future solar systems. 1,350 light-years away. The light you see from the Orion Nebula tonight left there when the Roman Empire was collapsing, when the Tang dynasty was rising in China, when the Mayan civilization was at its height. The Milky Way contains stellar remnants, the corpses of dead stars. When a star like the Sun exhausts its fuel, it swells into a red giant, sheds its outer layers, and leaves behind a white dwarf. White dwarfs are incredibly dense, packing about half the Sun's mass into a sphere the size of Earth. A teaspoon of white dwarf material would weigh about 5 tons. White dwarfs don't generate energy through fusion. They're hot simply because they were once the cores of stars, and they're slowly cooling over billions of years. Eventually, they'll fade to black dwarfs, cold and dark. though the universe isn't old enough yet for any black dwarfs to exist. More massive stars die in more spectacular fashion. When they exhaust their fuel, they can't support themselves against gravity, and they collapse catastrophically. The collapse rebounds in a supernova explosion, one of the most energetic events in the universe. For a few weeks, a supernova can outshine an entire galaxy. After a supernova, what's left depends on the star's mass. If the core is between about 1.4 and 3 solar masses, it becomes a neutron star, an object so dense that a teaspoon of it would weigh 1 billion tons. Neutron stars are made almost entirely of neutrons, packed together so tightly that the entire star is essentially a single atomic nucleus the size of a city. If the core is more than about 3 solar masses, even neutrons can't resist gravity. The core collapses into a black hole, a region of space-time where gravity is so strong that not even light can escape. Black holes are tears in the fabric of space, singularities where the laws of physics break down. The Milky Way contains millions of black holes. Most are stellar mass black holes, the remnants of massive stars. They lurk throughout the galaxy, invisible unless they're actively pulling in material. When matter falls into a black hole, it heats up and emits X-rays, which we can detect. That's how we find them. The nearest known black hole to Earth is about 1/600 light-years away. It's part of a binary system, orbiting a visible star. The black hole itself is invisible, but astronomers can detect its presence from the motion of its companion star. 1,600 light-years, close by galactic standards, and yet there's no danger. Black holes don't roam around devouring everything. They're not cosmic vacuum cleaners. They have the same gravitational pulls as the star that formed them. If the sun suddenly became a black hole, Earth's orbit wouldn't change. We'd just freeze in the darkness. The Milky Way has experienced bursts of star formation throughout its history. Sometimes the rate increases dramatically, triggered by collisions with other galaxies or by the infall of fresh gas. Other times it slows down as gas is consumed or blown away by stellar winds and supernova. The galaxy's history is written in its stars. By studying the ages and compositions of different stellar populations, astronomers can reconstruct what happened billions of years ago. It's like archaeology, but instead of digging through dirt, we're sifting through starlight. The Milky Way is not perfectly symmetrical. One side of the galactic disk is slightly warped, tilted up on one side and down on the other. This warp might be caused by the gravitational influence of satellite galaxies or by a past collision. It's subtle but measurable. The galaxy also has ripples in its disk, like waves on a pond. These ripples might have been caused by a dwarf galaxy passing through the disk millions of years ago, sending stars bobbing up and down like ripples on water. The galaxy is still settling from that encounter. The Milky Way's satellite galaxies are small compared to the main galaxy, but they're important. The largest satellite is the Large Magellanic Cloud, a dwarf galaxy visible from the southern hemisphere. It contains about 30 billion stars and orbits the Milky Way at a distance of about 160,000 light-years. The Large Magellanic Cloud is slowly being torn apart by the Milky Way's gravity. In a few billion years, it will merge with our galaxy, adding its stars to the Milky Way's collection. Its companion, the Small Magellanic Cloud, will likely suffer the same fate. Both Magellanic Clouds are visible to the naked eye from the southern hemisphere. They look like detached pieces of the Milky Way, glowing patches in the night sky. Indigenous peoples in the southern hemisphere have known about them for thousands of years, weaving them into their mythologies and stories. The Milky Way's oldest stars are about 13 billion years old, nearly as old as the universe itself. These ancient stars formed from the primordial gas that filled the early universe, gas that contained almost no heavy elements. They're metal poor, made mostly of hydrogen and helium. By studying these old stars, astronomers can learn about the conditions in the early universe. They're time capsules, carrying information from epochs we can never directly observe. Some of these stars might have planets, though we haven't found any yet. It's hard to imagine what a planet would be like orbiting a 13 billion-year-old star. The Milky Way's youngest stars are being born right now, in nebulae scattered throughout the galaxy. Some of these protostars are less than 1 million years old. They're still gathering mass, still wrapped in their birth clouds. They haven't even begun fusion yet. From 13 billion years old to less than 1 million, the Milky Way contains the full spectrum of stellar ages. It's a living archive of cosmic history, a chronicle written in light and gravity. The Milky Way is a barred spiral galaxy, type SBC in the Hubble classification system. The S stands for spiral, the B for barred, and the C indicates that the spiral arms are loosely wound and the central bulge is relatively small. If you could see the Milky Way from outside, it might look similar to other SBC galaxies like NGC 1300 or NGC 1365. But of course, we can't see the Milky Way from outside. We're stuck inside it, trying to map its structure from within. It's like trying to draw a map of a city while standing in the middle of it, unable to move. You can see the buildings nearby, but the overall layout is harder to discern. Astronomers have mapped the Milky Way using various techniques. Radio observations reveal the distribution of hydrogen gas. Infrared observations peer through dust to see obscured stars. Optical observations catalog visible stars and measure their distances. Slowly, piece by piece, we're building a complete picture of our galaxy. The Milky Way's disk is not empty space. It's filled with gas, dust, and plasma. The total mass of this interstellar medium is roughly 10 billion solar masses, about 10% of the total mass in stars. Most of it is hydrogen, but there's also helium, carbon monoxide, carbon, oxygen, and trace amounts of heavier elements. This interstellar medium is the raw material for future generations of stars. It's being constantly recycled. Stars form from it, live their lives, and then return most of their mass back to the interstellar medium when they die. Supernovae scatter heavy elements, enriching the gas for the next generation. The Milky Way is a cosmic recycling system. The carbon in your body was forged inside a star billions of years ago. That star exploded, scattering its carbon into space. Eventually, that carbon found its way into the clump that formed the sun and Earth. And now, here you are, a temporary arrangement of stardust, thinking about the galaxy that made you. We are all made of star stuff, as Carl Sagan famously said. It's not poetic exaggeration. It's literally true. The Milky Way contains massive molecular clouds, vast regions of cold, dense gas where stars are born. The largest of these clouds can be millions of solar masses, spanning hundreds of light years. They're called molecular clouds because they're cold enough for atoms to bond together into simple molecules like hydrogen gas, H2, and carbon monoxide, CO. Inside these clouds, gravity pulls gas together into clumps. The clumps grow, pulling in more gas, heating up from the compression. When the temperature at the center reaches about 10 million degrees, nuclear fusion ignites, and a star is born. The process takes about 10 to 50 million years, depending on the star's mass. The Milky Way's spiral arms are partially defined by these molecular clouds. The arms are where gas is compressed by density waves, triggering star formation. Young, hot stars light up the arms, making them visible. Older stars drift between the arms, so the arms appear brighter even though they don't actually contain more stars. It's an elegant mechanism, a cosmic dance of gravity and gas and light. The Milky Way has a thick disk in addition to the thin disk. The thin disk is where most of the gas and young stars reside. The thick disk extends above and below the thin disk, populated by older stars with different motions and compositions. The thick disk might have formed during the galaxy's early history, perhaps from the merger with Gaia Enceladus. Above and below the disks, there's the galactic halo, a roughly spherical distribution of old stars and globular clusters. The halo extends far beyond the visible disk, blending gradually into intergalactic space. It's the oldest part of the galaxy, the first structure that formed when the Milky Way was assembling from smaller pieces. The Milky Way probably formed about 13 billion years ago, not long after the Big Bang. It started as a cloud of gas enriched slightly with heavy elements from the very first generation of stars. Gravity pulled the gas together and it began to collapse. As it collapsed, it started rotating, spinning faster and faster, like a figure skater pulling in their arms. The rotation flattened the cloud into a disk. Gas in the disk continued to form stars. Smaller galaxies merged with the growing Milky Way, adding their stars and gas. Over billions of years, the galaxy grew into the structure we see today. But that structure is still evolving. The Milky Way will look different a billion years from now, and different again a billion years after that. The Milky Way's visible mass is about 90 billion to 200 billion solar masses, but its total mass, including dark matter, is probably closer to 1 to 2 trillion solar masses. Of that mass is dark matter, invisible but gravitationally influential. This dark matter halo extends far beyond the visible stars, perhaps 600,000 light years or more from the Galactic Center. It's a vast, invisible structure, and we're embedded within it. Dark matter particles are passing through you right now, billions of them every second. But they interact so weakly with ordinary matter that you don't notice. The Milky Way's rotation curve is one of the key pieces of evidence for dark matter. Astronomers measure how fast stars and gas are moving at different distances from the galactic center. In a galaxy with only visible matter, you'd expect the rotation speed to decrease with distance, like planets in the solar system. But that's not what we see. The rotation speed stays roughly constant even at large distances. This can only be explained if there's a lot of invisible mass extending far beyond the visible stars. Dark matter provides that mass. It's the only explanation that fits the observations unless our understanding of gravity is fundamentally wrong. Some physicists have proposed modified theories of gravity to explain the rotation curves without dark matter. These theories, called MOND, modified Newtonian dynamics, and others adjust how gravity works at large scales. But so far, dark matter is the simpler explanation, and it fits more observations across the universe. The Milky Way is home to pulsars, rapidly spinning neutron stars that emit beams of radiation from their magnetic poles. As the pulsar spins, the beams sweep across space like lighthouse beams. If Earth happens to be in the path of the beam, we see a pulse of radio waves every time the beam sweeps past us. Pulsars were discovered in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge. She noticed strange periodic signals in her radio telescope data, pulses arriving with remarkable regularity. For a brief time, scientists wondered if they might be signals from an alien civilization. They even nicknamed the source LGM-1 for little green men. But further observations showed that pulsars were natural phenomena, neutron stars spinning at incredible speeds. Some pulsars rotate hundreds of times per second. The fastest known pulsar spins 716 times per second. It's a neutron star the size of a city, rotating faster than a kitchen blender. The regularity of pulsar pulses is astonishing. The best pulsars keep time more accurately than atomic clocks. They're natural cosmic metronomes, ticking away with precision across thousands of light years. The Milky Way contains magnetars, neutron stars with extraordinarily strong magnetic fields. A magnetar's magnetic field is so intense that it warps the very atoms around it. If you got within 1,000 kilometers of a magnetar, the magnetic field would disrupt the electromagnetic forces holding your body together. You wouldn't survive. Magnetars occasionally produce giant flares, sudden bursts of X-rays and gamma rays. One such flare in 2004 was detected from a magnetar about 50,000 light years away. The flare was so powerful that it affected Earth's upper atmosphere, even from that distance. For a tenth of a second, it was brighter than anything in the sky except the sun. 50,000 light years away, and it still reached us. The universe is filled with such violence, such energy, and yet here we are, safe in our quiet corner of the galaxy. The Milky Way has been observed by humans for as long as humans have existed. Ancient peoples saw that band of light and wove stories around it. The ancient Greeks saw spilled milk. The ancient Chinese saw a silver river. The Norse saw a path to Valhalla. The Maori saw a trail of stars. These stories remind us that we've always been looking up, always wondering, always trying to make sense of the cosmos. The technology changes, the understanding deepens, but the fundamental human impulse remains the same. The Milky Way is visible from Earth, but only if you're in a dark enough location. Light pollution from cities washes out the faint glow of distant stars. In major cities, you might see only a handful of the brightest stars. But travel to a remote location, away from artificial lights, and the sky transforms. In truly dark skies, the Milky Way is spectacular. It stretches across the heavens like a glowing river, bright enough to cast faint shadows. You can see dark lanes running through it, dust clouds blocking the light of stars behind them. You can see the bulge toward the Galactic Center, thicker and brighter than the rest. And you can see the sheer number of stars, not just hundreds, not just thousands, but so many stars that they blend together into a continuous glow. It's humbling, it's beautiful, it reminds you how small you are and how vast the universe is. The Milky Way's appearance changes with the seasons. In the northern hemisphere during summer, the Galactic Center is visible in the southern sky, in the constellations Sagittarius and Scorpius. This is the brightest part of the Milky Way, the densest concentration of stars. In winter, we see the opposite direction, looking out toward the galactic edge. It's dimmer, less spectacular, but still beautiful. From the southern hemisphere, the view is different. The Galactic Center passes nearly overhead during winter months. The Magellanic Clouds are visible year-round. It's a different sky, a different perspective on our galaxy. The Milky Way contains open star clusters, loose groups of stars that form together from the same molecular cloud. Unlike globular clusters, which are old and tightly packed, open clusters are young and loosely bound. They contain anywhere from a few dozen to a few thousand stars. The Pleiades, or Seven Sisters, is one of the most famous open clusters. It's visible to the naked eye as a small group of stars in the constellation Taurus. Most people can see 6 or 7 stars, though the cluster actually contains over 1,000. The Pleiades formed about 100 million years ago, making it young by cosmic standards. Open clusters don't last forever. Over hundreds of millions of years, gravitational interactions with other stars and molecular clouds gradually tear them apart. The stars drift away, becoming indistinguishable from the general stellar population. Most stars in the galaxy, including our Sun, probably formed in open clusters that have long since dissolved. The Sun might have had siblings once, hundreds or thousands of stars born from the same cloud. But they've scattered across the galaxy over the past 4.6 billion years. They're out there somewhere, carrying the same chemical signature, the same composition, but we don't know where they are. The Milky Way's interstellar dust is not like dust on Earth. It's composed of tiny grains, typically less than a micrometer across, made of carbon, silicon, oxygen, and other elements. These grains form in the atmospheres of cool stars and are scattered into space when the stars die. Interstellar dust affects how we see the galaxy. It absorbs and scatters light, making distant objects appear dimmer and redder than they actually are. This is called interstellar extinction. It's particularly problematic when trying to observe the Galactic Center, which is heavily obscured by dust. But dust also plays a crucial role in star formation. The dust grains provide surfaces where hydrogen atoms can combine into molecules. They shield the interior of molecular clouds from starlight, allowing the gas to cool and collapse. Without dust, star formation would be much less efficient. The Milky Way stars come in many varieties. There are red dwarfs, small and cool, burning their fuel so slowly they could last trillions of years. There are stars like our Sun, medium-sized and yellow, with lifetimes of about 1 to 10 billion years. There are blue giants, massive and hot, burning bright and dying young after just a few million years. The most massive stars in the Milky Way can be more than 100 times the mass of the Sun. They burn so hot that their surfaces glow blue-white, with temperatures exceeding 40,000 degrees. They live fast and die young, exploding as supernovae after just a few million years. The least massive stars, the red dwarfs, can be as little as 8% of the Sun's mass. They're so cool that their surfaces glow red, with temperatures around 3,000 degrees. They're incredibly common, making up about 70% of all stars in the galaxy, but they're so dim that not a single red dwarf is visible to the naked eye from Earth. The closest star to our Sun is Proxima Centauri, a red dwarf about 4.24 light-years away. It's part of the Alpha Centauri system, a triple star system that includes 2 Sun-like stars. Proxima Centauri is so dim that it wasn't discovered until 1915, even though it's our nearest stellar neighbor. 4.24 light-years. That's the closest another star comes to us. Light takes more than 4 years to cross that gap. The fastest spacecraft we've built, Voyager 1, is moving at about 38,000 miles per hour relative to the Sun. At that speed, it would take more than 1,000 years to reach Proxima Centauri. Space is vast. Even our nearest neighbors are impossibly far away by human standards. Proxima Centauri has at least 2 known planets. One of them, Proxima Centauri b, orbits in the star's habitable zone. It's slightly more massive than Earth and might have liquid water on its surface. Of course, there are complications. Proxima Centauri is a flare star prone to violent eruptions that could strip away a planet's atmosphere. Whether life could survive, there is an open question, but it's tantalizing. The nearest star to our own might have a habitable planet. It might have liquid water. It might even have life. We don't know. And with current technology, we have no way to find out. The Milky Way's spiral structure is not static. It's dynamic, constantly evolving. Stars orbit the Galactic Center at different speeds depending on their distance. The spiral arms are density waves that rotate at a different speed than the stars themselves. Stars drift into the arms, brighten them temporarily, and then drift out again. This creates a pattern that persists even though the individual components are constantly moving. It's like the wave pattern you see when you snap a rope. The wave moves along the rope, but the rope itself doesn't travel with it. The exact mechanism that maintains the spiral structure is still debated. Density waves driven by gravitational instabilities are the leading explanation, but the details are complex, involving interactions between stars and dark matter. The Milky Way has regions called HII regions, clouds of ionized hydrogen gas. These regions glow brightly because they're lit up by hot young stars embedded within them. The ultraviolet light from these stars is energetic enough to strip electrons from hydrogen atoms, ionizing the gas. When the electrons recombine with protons, they emit light, creating the characteristic red glow of HII regions. The Orion Nebula, which we mentioned earlier, is an HII region. So is the Carina Nebula, the Lagoon Nebula, and the Eagle Nebula. These are some of the most photogenic objects in the galaxy, popular targets for astrophotographers. The Milky Way's chemical composition has evolved over time. In the beginning, just after the Big Bang, the universe contained only hydrogen, helium, and traces of lithium. No carbon, no oxygen, no iron. All the heavier elements were created later inside stars. Stars are nuclear furnaces. In their cores, they fuse light elements into heavier ones. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. In massive stars, the process continues, creating neon, magnesium, silicon, and eventually iron. But fusion stops at iron. Fusing iron requires energy rather than releasing it. So when a massive star's core fills with iron, fusion ceases. The core collapses, triggering a supernova. The explosion is so energetic that it creates elements heavier than iron, like gold, platinum, and uranium. All of these elements are scattered into space by the supernova. They mix with the interstellar medium, enriching it. The next generation of stars forms from this enriched gas, containing more heavy elements than the previous generation. This process has been going on for billions of years. Each generation of stars adds more heavy elements to the galaxy. Astronomers call this process chemical evolution, and it's why newer stars like our Sun contain more heavy elements than ancient stars formed 13 billion years ago. The Milky Way contains supernovae remnants, the expanding debris clouds from exploded stars. One of the most famous is the Crab Nebula, the remnant of a supernova that was observed in 1054 AD. Chinese and Arab astronomers recorded a guest star that appeared in the constellation Taurus, bright enough to be visible during the day for several weeks. Today, the Crab Nebula is about 11 light-years across and still expanding. At its center is a pulsar, the remnant of the star's core, spinning 30 times per second. The pulsar powers the nebula, pumping energy into it and causing it to glow. Supernova remnants are important. They inject energy into the interstellar medium, stirring it up and triggering new waves of star formation. They also enrich the medium with heavy elements. The calcium in your bones, the iron in your blood, the oxygen you breathe. All of it came from supernova explosions. The Milky Way experiences supernovae regularly, though not as frequently as some galaxies. On average, a supernova occurs in the Milky Way about once every 50 to 100 years. Most of them are obscured by dust and occur too far away to be visible to the naked eye. The last supernova visible without a telescope was Kepler's supernova in 1604. We're overdue for another nearby supernova. Statistically, one should occur every century or so, and it's been more than 400 years. When the next one happens, it will be a spectacular sight, potentially brighter than Venus, visible even during the day. But predicting when and where is difficult. We know which stars are candidates. Betelgeuse, the red supergiant in Orion, is near the end of its life and could explode any time within the next 100,000 years. Eta Carinae, a massive star about 7,500 light-years away, is highly unstable and could go supernova soon, but soon in cosmic terms could mean tomorrow, or could mean 10,000 years from now. The Milky Way has stellar streams, narrow ribbons of stars stretching across the sky. These are the tidal remnants of globular clusters or dwarf galaxies that have been torn apart by the galaxy's gravity. The stars from these disrupted objects continue orbiting the Milky Way, but now they're spread out in long, thin trails. One of the most prominent stellar streams is the Sagittarius stream, the remnant of the Sagittarius dwarf elliptical galaxy. This dwarf galaxy is being torn apart by the Milky Way right now in real time. Its stars are scattered in loops around the galaxy, marking its orbital path. These streams are useful for understanding the Milky Way's gravitational field and dark matter distribution. By tracking how the streams move, astronomers can infer the shape and strength of the galaxy's gravity, including the contribution from dark matter. The Milky Way is too faint to see with the naked eye during a full moon. The moon's light washes out the faint glow of distant stars. Even a quarter moon can make the Milky Way difficult to see. For the best views, you want a new moon, or at least a crescent moon that sets early in the evening. You also want to avoid the hours around midnight when the zodiacal light can interfere. The zodiacal light is sunlight reflecting off dust in the solar system, creating a faint glow along the ecliptic. It's subtle, but in truly dark skies, it can be noticeable. The best time to see the Milky Way is during the hours before dawn or after dusk, when the sky is fully dark, but the zodiacal light is below the horizon. And of course, you want to be far from city lights, in a location with minimal light pollution. The Milky Way's luminosity is about 25 billion times the sun's luminosity. That's the total light output from all the stars, gas and dust in the galaxy. It sounds like a lot, and it is. But compared to some galaxies, the Milky Way is actually fairly modest. Some elliptical galaxies contain trillions of stars and can be hundreds of times more luminous than the Milky Way. Quasars, powered by supermassive black holes actively feeding on matter, can outshine the entire Milky Way by factors of thousands or even millions. But the Milky Way is bright enough. It's our home, and it's beautiful in its own right. The Milky Way will eventually merge with Andromeda, as we mentioned earlier. But that merger is still billions of years away. In the meantime, the two galaxies are approaching each other at about 250,000 miles per hour. That sounds fast, but over the 2.5 million light-years separating them, it translates to a collision in about 4 to 5 billion years. When the merger happens, it will be a slow, graceful process. The galaxies will pass through each other the first time, barely interacting. But gravity will pull them back together for a second pass, and then a third. Each pass will be more chaotic than the last as the two galaxies become increasingly entangled. Eventually, after hundreds of millions of years, they'll settle into a single, larger elliptical galaxy. The spiral structure of both galaxies will be destroyed. The stars will be scattered into a more spherical distribution, and the two supermassive black holes at the centers of the galaxies will eventually merge, creating an even larger black hole. By the time this happens, the sun will be near the end of its life. It will have swollen into a red giant, possibly engulfing Mercury and Venus. Earth might survive, but its oceans will have boiled away. The planet will be a scorched, dead world. But the merger itself won't be a problem. The stars are so far apart that direct collisions will be incredibly rare. The sun and its planets will simply end up in a different orbit in the new galaxy. Assuming anyone is still around to see it, the night sky will look very different. Instead of the Milky Way's spiral structure, they'll see the diffuse glow of an elliptical galaxy. The Milky Way has inspired countless myths and legends. The ancient Hindus saw it as the path of the gods. The ancient Armenians saw it as straw scattered by a thief fleeing with stolen grain. The ancient Japanese saw it as a river separating two lovers, crossed only once a year. These stories reflect a deep human need to understand our place in the cosmos. We look up and see patterns, and we create narratives to explain them. The stories change, but the impulse remains constant. The Milky Way is moving within the local group. The local group itself is moving toward the Virgo cluster, and the Virgo cluster is being pulled toward the Great Attractor. It's motion within motion within motion, a cosmic ballet of gravitational attraction and inertia. And yet, from our perspective, everything seems stable. The stars remain in their constellations. The planets follow their orbits. The moon rises and sets. The motion is so vast, so slow that we can't perceive it directly. We have to measure it carefully, using telescopes and spectrographs and patient observation. The Milky Way contains hypervelocity stars, stars moving fast enough to escape the galaxy's gravity. These stars are rare, but they exist. Most of them were probably flung out by close encounters with the supermassive black hole at the Galactic Center. A binary star system wanders too close. One star is captured into orbit around the black hole. The other is flung outward at incredible speed, fast enough to escape the galaxy entirely. Some hypervelocity stars are moving at more than 1,000 kilometers per second. That's about 2.2 million miles per hour. At that speed, they'll leave the Milky Way and drift through intergalactic space, becoming lonely wanderers between galaxies. The Milky Way has a vertical structure in addition to its spiral structure. The disk is thin, but it has thickness. Stars bob up and down as they orbit, oscillating above and below the galactic plane. The sun oscillates with a period of about 70 million years, passing through the plane every 35 million or so. Some scientists have speculated that these oscillations might correlate with mass extinctions on Earth. The idea is that when the solar system passes through the plane, it encounters more molecular clouds and comets, increasing the risk of impacts. But the evidence for this connection is weak. Mass extinctions seem to be more random than periodic. The Milky Way's star formation rate has decreased over time. Billions of years ago, when the galaxy was young and gas-rich, stars formed much more rapidly. Today, the rate has slowed to about 3 to 7 new stars per year. In the future, it will slow even further as the galaxy runs out of gas. Eventually, in about 1 trillion years, star formation will cease entirely. The Milky Way will become a red and dead galaxy, populated only by old, dim stars and stellar remnants. But that's so far in the future that it's almost meaningless. 1 trillion years is about 70 times longer than the current age of the universe. The Milky Way has a thin layer of gas called the circumgalactic medium, extending far beyond the visible disk. This gas is hot, heated to millions of degrees by supernovae and stellar winds. It's incredibly diffuse, containing only a few atoms per cubic centimeter. But there's so much volume that the total mass is significant. This circumgalactic medium is a reservoir of gas that can fall back onto the galaxy, replenishing the supply for star formation. It's also where gas expelled from the galaxy ends up. Supernovae and stellar winds blow gas out of the disk. Some of it escapes entirely, but much of it ends up in the circumgalactic medium, where it cools and eventually falls back. The Milky Way's rotation is complex. The stars, cloud and dust don't all rotate at the same rate. The inner regions rotate faster than the outer regions, but not by as much as you'd expect based on Kepler's laws. This is called differential rotation, and it's one of the things that creates and maintains the spiral structure. The bar at the center rotates even more strangely. It's a solid body rotation, meaning the whole bar rotates together like a spinning rod. This is different from the disk, where each orbit has its own period. The bar completes one rotation every 120 million years or so. The Milky Way has been photographed by spacecraft, but only partially. You can't take a picture of the entire galaxy from within it. But missions like the Hubble Space Telescope and the Gaia spacecraft have mapped large portions of the sky, creating detailed catalogs of stars. The Gaia mission in particular has revolutionized our understanding of the Milky Way. Launched in 2013, Gaia has measured the positions, distances, and motions of more than 1 billion stars with unprecedented precision. This data has allowed astronomers to map the galaxy's structure in 3 dimensions, revealing details that were previously invisible. Gaia has discovered new stellar streams, refined our estimate of the distance to the Galactic Center, and even detected subtle ripples in the galactic disk. It's rewritten our understanding of the Milky Way's history and structure. The Milky Way contains variable stars, stars whose brightness changes over time. Some vary because they pulsate, swelling and shrinking periodically. Others vary because they're eclipsed by a companion star. Still others vary erratically due to instabilities in their atmospheres or accretion disks. One important class of variable stars is the Cepheid variables, stars that pulsate with a period related to their intrinsic brightness. This makes them excellent distance indicators. By measuring a Cepheid's period, you can determine its true brightness. By comparing that to its apparent brightness, you can calculate its distance. Cepheids were crucial in determining the scale of the universe. In the 1920s, Edwin Hubble used Cepheid variables to measure the distance to Andromeda, proving that it was far outside the Milky Way and that other galaxies existed. This fundamentally changed our understanding of the cosmos. The Milky Way's halo contains ancient stars with unusual compositions. These stars form from gas that hadn't been heavily enriched with heavy elements yet. Some of them have iron abundances less than 1/1000th that of the Sun. They're fossils from the early universe, time capsules preserving information about conditions billions of years ago. Studying these metal-poor stars helps astronomers understand the formation of the first elements, the nature of the first supernova, and the assembly of the first galaxies. Every such star is precious, a unique window into an epoch we can't observe directly. The Milky Way has a vertical thickness that varies with distance from the center. Near the center, the disk is thicker, puffed up by the bar and by old stellar populations. Farther out, the disk thins. At the Sun's location, the thin disk is about 1,000 light-years thick, while the thick disk extends about 3,000 light-years above it and below the plane. Stars in the thick disk are older and move faster vertically than stars in the thin disk. They have more random motion, less organized rotation. This suggests they formed earlier, when the galaxy was less settled, or that they were heated by some event, perhaps the merger with Gaia Enceladus. The Milky Way has served as a laboratory for understanding galaxies in general. We can study it in much more detail than any other galaxy because we're inside it. We can resolve individual stars, measure their compositions, track their motions. This detailed knowledge helps us interpret observations of distant galaxies where we can't see such fine details. In many ways, the Milky Way is our Rosetta Stone for galactic astronomy. It's the standard against which other galaxies are compared, the template for understanding spiral galaxies throughout the universe. The Milky Way's mass is still uncertain. Different measurement techniques give different results, ranging from about 700 billion to 2 trillion solar masses. The uncertainty comes mostly from the dark matter halo, which is difficult to measure directly. We can only infer its presence from gravitational effects. Recent measurements using the motions of satellite galaxies and stellar streams suggests the Milky Way's mass is probably around 1 to 1.5 trillion solar masses. That makes it roughly comparable to Andromeda in mass, though Andromeda might be slightly more massive. The Milky Way is not the largest galaxy in the local group. That distinction belongs to Andromeda, which is somewhat bigger and more massive. But the Milky Way is respectably sized. It's a substantial spiral galaxy, not a giant but not a dwarf either. It's comfortably in the middle of the size distribution for galaxies. The Milky Way has inspired art, literature, and music for thousands of years. It's appeared in paintings, poems, songs, and stories. It's been a symbol of mystery, beauty, infinity, and the divine. Different cultures have interpreted it differently, but all have recognized its significance. In modern times, the Milky Way has taken on new meaning. It represents our cosmic address, our place in the universe. It's a reminder that Earth is just one planet among billions, orbiting one star among hundreds of billions, in one galaxy among hundreds of billions. And yet, it's also a reminder of connection. Everything in the Milky Way is connected by gravity, by chemistry, by history. The stars are family, distant cousins born from the same primordial gas. We're all part of the same cosmic ecosystem. The Milky Way will be here long after we're gone, long after humanity has vanished, long after the sun has died. The galaxy will continue its slow rotation. Its stars will continue their orbits. Its black hole will continue its patient wait at the center. Galaxies live on timescales that dwarf human comprehension. Our entire recorded history, all of human civilization, is less than 0.1% of the Milky Way's age. We're a brief flicker in the galaxy's long story, and still we're here. We're part of it. We're made of atoms forged in the hearts of dying stars, scattered across the galaxy, gathered together on one small planet, arranged by chance and chemistry and evolution, into beings that can look up and understand. Think about that. The Milky Way is visible from almost everywhere on Earth, if the conditions are right. From the equator, you can see the entire galactic plane over the course of a year. From the poles, you see only part of it. But what you see never sets. It's always there, circling the horizon. Light pollution is the enemy of the Milky Way. In developed countries, most people live in areas where they can't see it. The artificial light from cities and towns washes out the faint glow of distant stars. You have to travel to remote areas, away from civilization, to see the galaxy in its full glory. This is a loss. For most of human history, everyone could see the Milky Way. It was part of the night sky, as familiar as the moon. Now, many people have never seen it. They've never experienced that profound sense of scale and beauty that comes from looking up at the galactic plane stretching across the heavens. Some organizations are working to preserve dark skies, to create refuges where future generations can experience the night sky as our ancestors did. It's an uphill battle, but it's important. The Milky Way is our heritage, our home. Everyone should have the chance to see it. The Milky Way contains brown dwarfs, objects that are too massive to be planets, but too small to be stars. They're sometimes called failed stars. They form like stars from collapsing clouds of gas, but they never accumulate enough mass to ignite hydrogen fusion. Instead, they just glow faintly from the heat of their formation, slowly cooling over billions of years. Brown dwarfs are difficult to detect because they're so dim, but surveys, particularly infrared surveys, have found thousands of them. They might be surprisingly common, perhaps comparable in number to stars, but because they're so faint, we're still discovering them. The boundary between the largest planets and the smallest brown dwarfs is fuzzy. Both can have similar masses, similar compositions. The distinction is usually based on how they formed. If it formed by collapsing from a cloud, it's a brown dwarf. If it formed by accretion in a disk around a star, it's a planet. The Milky Way has witnessed unimaginable violence over its long history. Stars have exploded. Black holes have formed. Galaxies have collided and merged. And yet, through it all, the galaxy has persisted, growing and evolving, but never destroyed. This resilience is remarkable. Despite all the Despite all the energy being released, the galaxy as a whole remains stable. Gravity holds it together. The slow, patient pull of gravity overcomes even the most violent explosions. The Milky Way has taught us that the universe is both violent and stable, chaotic and ordered. It's a place of extremes where black holes and baby stars coexist, where destruction and creation happen side by side. The Milky Way's future is uncertain in detail, but the broad outline is clear. It will merge with Andromeda. Star formation will eventually cease. The stars will slowly burn out. The galaxy will fade. But that's trillions of years from now. For now, the Milky Way is alive and vibrant. Stars are being born. Planets are forming. And somewhere in this vast spiral, on one small planet, beings have arisen who can look up and understand what they're seeing. We are the Milky Way becoming conscious of itself. We are stardust contemplating stars. And that's a profound and beautiful thing. Let your mind rest on that thought. Let it settle like dust on an ancient moon. The Milky Way is vast and old and full of mystery, and you're part of it. Every atom in your body came from this galaxy. You're not separate from it. You're woven into its fabric, a temporary pattern in the cosmic tapestry. Maybe that's comforting, maybe it's overwhelming, maybe it's both, but it's true in the deepest sense. You are the Milky Way, and the Milky Way is you. The Milky Way contains planetary nebula, beautiful shells of gas ejected by dying sun-like stars. Despite their name, they have nothing to do with planets. The name comes from early telescopes where these objects appeared as round, planet-like disks. But they're actually the outer layers of stars, blown off during the red giant phase. When a sun-like star exhausts its nuclear fuel, it swells into a red giant, expanding to hundreds of times its original size. Eventually, the outer layers become so loosely bound that they drift away into space, leaving behind a hot, exposed core. This core, a white dwarf, illuminates the expanding shell of gas, causing it to glow in beautiful colors. The Ring Nebula in Lyra is a famous example. Through a telescope, it looks like a cosmic smoke ring, a perfect circle of glowing gas. The nebula is about a light year across and still expanding. In a few tens of thousands of years, it will dissipate, fading into the interstellar medium. Our sun will create its own planetary nebula someday, about 5 billion years from now. It will swell, consume Mercury and Venus, and then shed its outer layers. The Earth, if it survives, will orbit a white dwarf in a system surrounded by a glowing shell of gas. It will be beautiful in a way. But there will be no one here to see it. The Milky Way's disk contains something called the local bubble, or the local cavity. It's a region about 1,000 light-years across where the interstellar medium is less dense than usual. We're inside this bubble, along with several hundred other stars. The local bubble was probably created by supernovae. About 10 to 20 million years ago, a cluster of massive stars formed nearby. Over time, these stars exploded as supernova, one after another. Each explosion blew gas outward, creating an expanding cavity. Eventually, these cavities merged, creating the large bubble we see today. The edge of the bubble is marked by denser gas and active star formation. We're floating through the relatively empty interior, like living inside a cosmic soap bubble. It's quieter here, calmer, with less radiation and fewer disturbances than you'd find in denser regions of the galaxy. The Milky Way has taught us about the life cycles of stars. We've learned that stars are born from gas clouds, live out their lives fusing hydrogen into helium and heavier elements, and then die in ways that depend on their mass. Small stars fade gently, massive stars explode violently, and the very largest stars might collapse directly into black holes without even producing a visible supernova. This understanding came gradually over centuries. Early astronomers thought stars were eternal, unchanging points of light, but observations reveal that stars vary, that they evolve, that they're born and die like living things. The timescales are vast, but the processes are real. The Milky Way contains Wolf-Rayet stars, massive stars that have stripped away their outer hydrogen layers, exposing their hot helium cores. These stars are incredibly bright and hot, with surface temperatures exceeding 100,000 degrees. They blow fierce stellar winds, losing mass rapidly as they race toward the end of their lives. Wolf-Rayet stars don't last long. They burn so intensely that they exhaust their fuel in just a few 100,000 years. Most will end as supernovae, and some might collapse directly into black holes. They're rare, with only a few hundred known in the entire Milky Way, but they're important contributors to the chemical enrichment of the galaxy. The Milky Way's spiral arms contain regions where multiple generations of stars have formed in succession. A molecular cloud collapses, forming massive stars. These stars live briefly and explode as supernovae. The shock waves from the explosions compress nearby gas, triggering a new wave of star formation. This process can repeat several times, creating chains of progressively younger star clusters. Astronomers call this sequential star formation, and it's part of what makes spiral arms so bright and active. The arms are not just places where stars happen to gather. They're places where stars are constantly being created, generation after generation. The Milky Way has stellar associations, loose groups of young stars that form together but aren't gravitationally bound. Unlike open clusters, which stay together for hundreds of millions of years, associations disperse within a few tens of millions of years. The stars drift apart, becoming indistinguishable from the general population. The nearest stellar association to Earth is the Scorpius-Centaurus association, about 380 to 470 light-years away. It contains thousands of young stars, including many that are visible to the naked eye. These stars formed over the past 15 million years and are gradually spreading out across the sky. The Milky Way's rotation has been measured precisely using pulsars. Pulsars act as natural clocks, emitting radio pulses with extraordinary regularity. By tracking how these pulses change over time, astronomers can measure the pulsar's motion. Combining measurements from many pulsars gives a detailed picture of the galaxy's rotation. This work revealed that the Milky Way's rotation is more complex than simple differential rotation. There are local variations, streams of stars moving together, and regions where the rotation deviates from the expected pattern. The galaxy is a dynamic, evolving system, not a static structure. The Milky Way contains X-ray binaries, systems where a normal star orbits a compact object like a neutron star or black hole. As matter from the normal star falls onto the compact object, it heats up to millions of degrees and emits X-rays. These systems can be incredibly bright in X-rays, sometimes outshining entire galaxies. Some X-ray binaries are transient, flaring up suddenly when a large amount of matter falls onto the compact object, then fading back to invisibility. Others are persistent, shining steadily for years or decades. Both types teach us about accretion, the process by which matter falls onto dense objects. The Milky Way's stellar populations have been mapped in 3 dimensions using data from the Gaia spacecraft. This has revealed structures that were previously invisible, including stellar streams, overdensities, and gaps in the distribution. The galaxy is far more complex than we thought even a decade ago. One surprising discovery is that the Milky Way's disk is not flat. It's warped, like the brim of a hat. The warp becomes more pronounced farther from the Galactic Center, with the disk tilted up on one side and down on the other. The cause of this warp is still debated, but it might be due to gravitational interactions with satellite galaxies. The Milky Way has been used as a testbed for theories of galaxy formation and evolution. Simulations of galaxy formation are tested against what we observe in the Milky Way. If the simulations can reproduce the Milky Way structure, mass, and stellar populations, that gives us confidence that they're capturing the essential physics. These simulations have become increasingly sophisticated, incorporating dark matter, gas dynamics, star formation, supernovae feedback, and black hole growth. Modern simulations can reproduce galaxies that look remarkably like the Milky Way, suggesting that we're on the right track in understanding how galaxies form. The Milky Way's central black hole, Sagittarius A, has been imaged directly. In 2022, the Event Horizon Telescope collaboration released an image showing the shadow of the black hole against the background of glowing gas. The image confirmed predictions from general relativity and provided direct visual evidence of the black hole's existence. The image shows a bright ring of emission surrounding a dark central region. The dark region is the black hole shadow, the area from which no light can escape. The bright ring is heated gas swirling around the black hole at close to the speed of light. It's remarkable that we can see this. The black hole is 26,000 light-years away and only 17 times the diameter of the Sun. Imaging it required linking radio telescopes around the world, creating a virtual telescope the size of Earth. The technical achievement is extraordinary. The Milky Way contains fast radio bursts, or at least some of them originate within our galaxy. FRBs are brief, intense pulses of radio emission that last only milliseconds. Most come from distant galaxies, but in 20, an FR was detected from a magnetar in the Milky Way. This discovery proved that magnetars can produce FRBs, solving a long-standing mystery. It also demonstrated that FRBs aren't always extragalactic phenomena. Some can occur relatively close to home. The Milky Way's stellar kinematics, the study of how stars move, has revealed the galaxy's complex history. Stars don't just orbit smoothly. Their motions record past events, disruptions, encounters with other galaxies. By analyzing stellar velocities, astronomers can reconstruct the galaxy's history, identifying merger events and disturbances. One such analysis revealed that the Milky Way's disk experienced a major disturbance about 2 to 3 billion years ago. Something, perhaps the Sagittarius dwarf elliptical galaxy passing through the disk, sent ripples through the stellar population. The stars are still ringing from that encounter, like a bell that was struck billions of years ago. The Milky Way has hierarchical structure, meaning it contains structures within structures. Stars cluster into groups, which cluster into associations and clusters, which cluster into spiral arms, which are part of the disk, which is part of the galaxy, which is part of the local group, which is part of Laniakea supercluster. This hierarchical organization is common in the universe. Gravity pulls matter together at all scales, creating nested structures from planets to superclusters. The Milky Way is just one node in this cosmic web. The Milky Way's oldest globular clusters contain stars that are nearly as old as the universe itself. These clusters formed within the first billion years after the Big Bang, during the era when the first galaxies were assembling. They're survivors from that ancient epoch, pristine time capsules floating through the galaxy. Some of these ancient stars show unusual chemical signatures. They contain elements in proportions that don't match anything we see today. This tells us that the first supernovae, the explosions that created the first heavy elements, were different from modern supernovae. They might have been more energetic, or they might have produced different elements. Every ancient star is a clue to understanding the early universe. Every measurement helps refine our theories of how the first stars formed and died. The Milky Way contains runaway stars, stars that were ejected from their birthplaces at high speed. Some were kicked out by supernovae explosions in binary systems. When one star in a binary explodes, the other star can be flung away at hundreds of kilometers per second. Other runaway stars were ejected from clusters by gravitational interactions. These stars are traveling through the galaxy at unusual speeds, often with trajectories that don't match the general rotation. They're cosmic outcasts wandering alone through space. The Milky Way's infrared appearance is very different from its optical appearance. Infrared light penetrates dust, so infrared images reveal stars and structures that are hidden in visible light. The Galactic Center, completely obscured in optical images, blazes brightly in infrared. Infrared surveys have mapped the Milky Way's structure in unprecedented detail, revealing the bar, the spiral arms, and the distribution of star-forming regions. These surveys have rewritten our understanding of the galaxy's morphology. The Milky Way has a vertical oscillation pattern in its disk. The Sun, for instance, bobs up and down relative to the galactic plane as it orbits. Right now, the Sun is about 60 light-years above the plane and moving upward. It will reach a maximum height of about 230 light years, then fall back down, passing through the plane and continuing to about 230 light years below it before reversing direction again. This oscillation has a period of about 70 million years. Some researchers have speculated that passages through the plane might correlate with geological or biological events on Earth, but the evidence is weak. The galaxy's influence on Earth is subtle at best. The Milky Way's satellite galaxies are being studied intensively for signs of dark matter. Dwarf galaxies are dominated by dark matter, with mass-to-light ratios far higher than normal galaxies. By studying their structure and dynamics, astronomers hope to learn more about dark matter's properties. Some dwarf galaxies are so dark matter-dominated that they're barely visible. They contain almost no stars, just faint wisps of light betraying the presence of an enormous dark matter halo. These ultra-faint dwarf galaxies are pushing the boundaries of detectability. The Milky Way has inspired the search for extraterrestrial intelligence. If the galaxy contains billions of habitable planets, and if even a tiny fraction developed life, and if even a tinier fraction developed intelligence, there could be millions of civilizations in the galaxy. Where are they? SETI, the search for extraterrestrial intelligence, has been scanning the skies for decades, looking for radio signals that could only be artificial. So far, nothing. The galaxy remains silent, or at least we haven't heard anything yet. Maybe we're not listening in the right way. Maybe advanced civilizations don't use radio. Maybe they're using communication methods we haven't imagined. Or maybe they're out there but choose not to transmit. The silence is puzzling, but it doesn't prove we're alone. The Milky Way's dust lanes are visible in photographs, dark ribbons cutting across the bright band of stars. These are dense clouds of dust blocking the light from stars behind them. They're not empty voids. They're full of material, just too cold and dense to emit visible light. In infrared and radio wavelength, these dust lanes light up, revealing complex structure and active star formation. What looks dark and empty in visible light is actually teeming with activity. The Milky Way has taught us humility. For most of history, humans believed we were at the center of everything. The Earth was the center of the universe. The sun and stars revolved around us, and everything was created for our benefit. But gradually, observation after observation, we were displaced. The Earth orbits the sun. The sun is just one star among billions. The Milky Way is just one galaxy among billions. We're not at the center. We're not special. We're ordinary, unremarkable, a typical planet around a typical star in a typical galaxy. And yet, there's something profound in that ordinariness. We're part of something vast and ancient. We're connected to the cosmos in ways our ancestors never imagined. The atoms in our bodies were forged in stars. We are, quite literally, children of the galaxy. The Milky Way's future collision with Andromeda has been simulated in detail. Computer models show the two galaxies approaching, passing through each other, pulling back together, and gradually merging. The simulations produce beautiful videos showing the dance of the galaxies over billions of years. These simulations suggest that the collision will trigger bursts of star formation as gas clouds collide and compress. The night sky will be spectacular, filled with brilliant new stars and glowing nebulae. But it will also be chaotic, with stars flung into new orbits and the overall structure of both galaxies destroyed. Eventually, after several billion years, the system will settle into a single elliptical galaxy. The simulations suggest it will be a fairly ordinary elliptical, not particularly remarkable. The merger will have consumed both beautiful spirals and produced something more mundane. But that's billions of years away. For now, the Milky Way and Andromeda are separate, each beautiful in its own right. The Milky Way contains emission nebulae, clouds of gas that glow because they're heated by nearby stars. The most famous is probably the Carina Nebula, a vast star-forming region about 7,500 light-years away. It contains some of the most massive stars known, including Eta Carinae, a star system so massive and unstable that it could explode as a supernova at any time. The Carina Nebula is breathtakingly beautiful. Images from the Hubble Space Telescope show when humans were just beginning to practice agriculture, when the first cities were being built in Mesopotamia. The Milky Way's magnetic field is weak but pervasive. It's generated by electric currents in the ionized gas that fills the galaxy. These currents are driven by the galaxy's rotation and by turbulence in the gas. The resulting magnetic field has a complex structure with reversals and twists that astronomers are still trying to map. Cosmic rays, high-energy particles traveling through the galaxy, are confined by this magnetic field. Without it, cosmic rays would escape the galaxy much more quickly. The magnetic field acts like a cage, keeping the particles trapped and bouncing around inside the galaxy. The Milky Way contains reflection nebulae, clouds of dust that don't emit light but reflect the light from nearby stars. The most famous is probably the nebulosity around the Pleiades star cluster. The young, hot stars in the Pleiades illuminate surrounding dust, creating a blue glow around the cluster. Reflection nebulae are blue because dust scatters blue light more efficiently than red light, the same reason Earth's sky is blue. The effect is subtle but beautiful, adding a ghostly glow to regions near young stars. The Milky Way has a nuclear star cluster at its very center, surrounding the supermassive black hole. This cluster is incredibly dense, with millions of stars packed into a region just a few light years across. Stars there are so close together that interactions and collisions might be common. Some stars in the nuclear cluster orbit the black hole at incredible speeds. The star S2, which we mentioned earlier, completes an orbit in just 16 years and reaches speeds up to 5,000 kilometers per second at its closest approach. That's about 1.7% of the speed of light. Observing these stars has allowed astronomers to test Einstein's theory of general relativity in extreme conditions. So far, Einstein's predictions hold up perfectly. The stars' orbits show the predicted effects of space-time curvature near the black hole. The Milky Way's gas is not uniformly distributed. It clumps into clouds at all scales, from small clouds a few light years across to giant molecular cloud complexes hundreds of light years across. The distribution is fractal-like, with structure at every scale. This clumpy structure affects star formation. Stars form in the densest clumps, where gravity can overcome the pressure of the gas. The efficiency of star formation, the fraction of gas that actually turns into stars, is surprisingly low. Only about 1% to 10 of the gas in a molecular cloud ends up in stars. The rest is blown away by stellar winds and supernovae before it can collapse. The Milky Way's stellar halo extends far beyond the disk, perhaps 300,000 light-years or more. The outermost stars are so distant that they're barely bound to the galaxy. They orbit slowly, taking hundreds of millions or even billions of years to complete one orbit. These distant stars are mostly metal-poor, ancient stars that formed early in the galaxy's history. Some might have been captured from dwarf galaxies that merged with the Milky Way. Each one carries information about the galaxy's past, about the conditions that existed billions of years ago. The Milky Way has been observed across the entire electromagnetic spectrum, from radio waves to gamma rays. Each wavelength reveals different aspects of the galaxy. Radio observations show cold hydrogen gas. Infrared shows dust and obscured stars. Visible light shows the stars themselves. X-rays reveal hot gas and high-energy processes. Gamma rays trace cosmic rays and exotic phenomena. By combining observations at all wavelengths, astronomers build a complete picture of the galaxy. It's like examining a specimen under different types of microscopes. Each view reveals something the others miss. The Milky Way contains protoplanetary disks, flat disks of gas and dust surrounding young stars. These disks are where planets form. Dust grains stick together, growing into pebbles, then boulders, then planetesimals, and finally planets. The process takes millions of years, but it's happening around thousands of young stars in the galaxy right now. The ALMA telescope array in Chile has imaged many protoplanetary disks in exquisite detail. The images show gaps and rings in the disks, structures carved by forming planets. We're watching planetary systems being born, seeing the process that created our own solar system 4.6 billion years ago. The Milky Way's oldest stars move in different patterns than younger stars. They have more random motion, less organized rotation. This is partly because they formed when the galaxy was less settled, and partly because they've been stirred up by gravitational interactions over billions of years. Astronomers divide stellar populations by their kinematics as well as their chemistry. Population we stars, young and metal-rich, orbit in the disk with low random velocities. Population 2 stars, old and metal-poor, have high random velocities and can be found in the halo as well as the disk. The Milky Way contains Wolf-Rayet binaries, systems where a Wolf-Rayet star orbits a companion star. These systems can be spectacular, with fierce stellar winds from both stars creating shock waves where they collide. Some Wolf-Rayet binaries produce periodic bursts of X-rays as material from one star falls onto the other. These systems are important laboratories for understanding stellar winds, mass transfer, and the evolution of massive stars. They're also potential progenitors of certain types of supernova and gamma-ray bursts. The Milky Way star formation history has been reconstructed from stellar populations. By determining the ages of stars throughout the galaxy, astronomers can measure how the star formation rate has changed over time. The results show that star formation was higher in the past, particularly 8 to 12 billion years ago during the galaxy's youth. Since then, the rate has gradually declined as the galaxy's gas supply has been consumed and expelled by stellar feedback. The Milky Way is middle-aged, past its peak star-forming years, but still active. The Milky Way has jets and outflows from the Galactic Center, streams of hot gas flowing outward from the vicinity of the supermassive black hole. These structures were discovered using X-ray and gamma-ray telescopes and are known as the Fermi bubbles. The Fermi bubbles extend about 25,000 light-years above and below the galactic plane. They might have been created by a burst of activity from Sagittarius A sometime in the past few million years, or they might be powered by star formation in the Galactic Center. Their exact origin is still debated. The Milky Way's chemical evolution can be traced through stellar abundances. By measuring the composition of stars of different ages, astronomers can see how the galaxy's metal content has increased over time. The oldest stars have almost no metals. Younger stars have more. The Sun, middle-aged at 4.6 billion years, has an intermediate abundance. This gradual enrichment is the signature of stellar nucleosynthesis and recycling. Each generation of stars adds more heavy elements to the interstellar medium, enriching the next generation. The Milky Way contains symbiotic stars, binary systems where a white dwarf orbits a red giant. The white dwarf accretes material from the red giant's stellar wind. This material heats up and emits radiation, particularly in ultraviolet and X-ray wavelengths. The systems can flare dramatically when accretion rates increase. Symbiotic stars are interesting because they're intermediate stages in binary evolution. They represent a phase between main sequence stars and more exotic systems like cataclysmic variables or type A supernova progenitors. The Milky Way has a vertical distribution of different stellar populations. Young stars are concentrated near the plane. Older stars have more vertical extent. The oldest stars fill the halo. This layering reflects the galaxy's assembly history and the different formation modes of different populations. Thin disk stars form from base that had settled into a thin rotating disk. Thick disk stars formed earlier, from base that was more turbulent and less settled. Halo stars formed earliest of all, before the galaxy had assembled into its current structure. The Milky Way continues to accrete material from its environment. Small galaxies are still falling in, adding their stars and gas to the Milky Way's inventory. The Magellanic Clouds are in the process of being tidally disrupted. The Sagittarius dwarf elliptical galaxy has already been partially consumed. This ongoing accretion is part of hierarchical structure formation. Large galaxies grow by consuming smaller ones. The Milky Way has been doing this for billions of years and will continue doing it for billions more. The Milky Way's destiny, in the very long term, is to merge with other galaxies in the local group, forming a single massive galaxy. This process will take tens of billions of years. By the time it's complete, the universe will be very different from today. Eventually, on even longer timescales, the merged galaxy will become isolated. The expansion of the universe will carry distant galaxies beyond the horizon, making them unobservable. The merged local group galaxy will be alone in an expanding void, its stars slowly burning out, the universe growing dark and cold around it. But that's so far in the future that it's almost meaningless to contemplate. Trillions of years, timescales that dwarf the current age of the universe. The Milky Way story is still in its early chapters. For now, we live in a vibrant galaxy, full of stars and gas and ongoing activity. Star formation continues. Planets are being born, and on at least one of those planets, beings have arisen who can look up and understand. We're part of this galaxy. We're made from its material, shaped by its environment, dependent on its stars for warmth and light. The Milky Way is not just our home. It's our parent, our creator, our context. Think about that for a moment. Let it settle in. You're not separate from the cosmos. You're an integral part of it. The galaxy flows through you. Every breath you take contains atoms from exploded stars. Every thought you think is powered by energy that originated in the sun's core. You are the Milky Way experiencing itself. You are a way for the cosmos to know itself, and that's extraordinary. Let that thought carry you now. Let yourself drift on it, like floating on a calm ocean under a star-filled sky. The Milky Way surrounds you, embraces you, holds you in its gravitational arms. You're safe here, cradled by the same forces that hold stars in their orbits. Rest now. Let the spiral arms turn slowly above you. Let the ancient starlight wash over you. Let the vast, patient rotation of the galaxy lull you into peaceful sleep. Where will we explore next? There are so many wonders still to discover, so many cosmic stories waiting to be told. But for tonight, this is enough. Tonight we have traveled through our home galaxy, touching on its beauty, its violence, its mystery, and its majesty. If these journeys through the cosmos bring you peace, consider subscribing to the Slumbering Archive. There are many more explorations waiting, many more gentle paths through the universe. Thank you for spending this time with me tonight. Thank you for your curiosity, your wonder, your willingness to contemplate the vast. The Milky Way is more magnificent because you're here to witness it. Sleep well, dream of stars, and remember that you're part of something ancient and beautiful and unfathomably large. Good night.